Today is the first of 2 weeks discussing acid-base equilibria. We're going to take the concepts that we learned regarding equilibrium in general and use those to look at various situations with acids and bases. First of all, we have to come to a definition of what an acid and a base is. The Arrhenius definition, which was probably now close to 200 years old, is that an acid is anything that ionizes to release hydrogen ions, and a base is anything that ionizes to release hydroxide ions. Subsequently, Bronsted and Lowry developed a theory that says that a compound that donates a proton to another compound is an acid. Now, you'll realize that a hydrogen ion is a proton. It is a hydrogen atom less the electron, so it's a proton. But this donation can either be in the form of another compound or in an ionization, and it also can be in the form of a combination with water, which we'll show in just a second. A Bronsted-Lowry base is any compound that accepts a proton from another compound. So quite a bit broader definition, particularly of a base, compared to that of the Arrhenius definition. Now in the future we will talk about Lewis acids and bases, and Lewis acid is anything that accepts a pair of electrons, and a Lewis base is anything that donates a pair of electrons. So here's a way of looking at acids and bases specifically from the vantage point of Bronsted-Lowry theory. And if you look at the top, you see that water, if you remove a hydrogen, you end up with if you remove a proton, you end up with the conjugate base of hydroxide. If you take at the same time ammonia and add a proton, you have the conjugate acid of the ammonium ion. So looking at the second line, the equation, you see that the acid, which is water, donates a proton to the base, which is ammonia, to form the conjugate base, which is the hydroxide ion, and the conjugate acid, which is the ammonium ion. Now the reason these are called conjugate base and conjugate acid is because if you look at the reaction in the opposite direction, that is from right to left, then the ammonium ion would donate a proton to the hydroxide ion. Thus, the ammonium ion would be an acid and the hydroxide ion would be a base. It's called conjugate because it's associated with the original acid, water, and the original base, ammonia. So the conjugate acid is the product that results when a base accepts a proton, and the conjugate base is the product that remains after an acid donates a proton. Because when the reaction goes in the opposite direction, their roles are swapped. So here's another example. You see HF, which is the acid, will donate a proton to water, which is the base, to form what's called the hydronium ion, which is the conjugate acid, and the conjugate base, which is the fluoride ion. Now the equilibrium constant for this reaction would be the concentration of hydrogen fluoride divided into the product of the concentration of the hydronium ion and the fluoride ion. The reason water is not included is water's a liquid that doesn't have a concentration, as you'll remember from our last week. So acid ionization is a reaction that occurs when a Bronsted-Lowry acid reacts with water and protons are transferred from the acid molecule to the water molecules. Here's another situation, similar situation. You have the base shown here as C5NH5. It's going to accept a proton from water, and in that case you'll have the conjugate acid, which is C5NH6 positive, and the hydroxide ion is the conjugate base, and the But the equilibrium constant is again shown, and it's the sum of it's the product of the products. It's the product of the concentration of the products divided by the concentration of the base. Again, water is not included because it is a liquid that has no concentration, or its concentration is 1. So this is an example of a base ionization, because what happens here is that the base accepts a proton from water and forms the conjugate acid and leaves the hydroxide ion as the conjugate base. Now water itself will ionize, and here's what you see. It's called autoionization. This is when a substance ionizes and one molecule of the substance reacts with another molecule of the same substance, forming a hydronium ion and a hydroxide ion base. Now in this situation, because on the reactant side the concentrations are both 1, the equilibrium constant for this is just the product of the two products, that is the hydronium ion times the concentration of the hydroxide ion. And that is called the ion product constant for water. And this is also called K sub W. It's the product of the hydronium ion concentration, the hydroxide ion concentration, and in the case of pure water, this is always equal to 1 times 10 to the minus 14. So in the background, this is always going on. When you have just pure water, this product is still true. Now, when you add an acid or a base to this situation, the product still remains true for water, and so it has to adjust in order to keep this product 1 times 10 to the minus 14. And I'll show you how that works in just a minute. This is a formula that you need to remember, that the product of the hydronium ion concentration times the product times the hydroxide ion concentration is always equal to 1 times 10 to the minus 14 at 25 degrees. Now this does change at different temperatures. You know that the equilibrium constant can change at different temperatures. And indeed, here's a problem where the ion product of water at 80 degrees is 2.4 times 10 to the minus 13. What are the concentrations of hydronium and hydroxide ions in pure water at 80 degrees? Well, let's look at how we would do that. Now at 25 degrees, I said that the Kw is 1 times 10 to the minus 14, and that was going to be equal to the product of the hydronium ion concentration times the hydroxide ion concentration. And in this situation, at 25 degrees, you would say that this x squared is going to equal 1 times 10 to the minus 14. So in pure water at 25 degrees, the concentration of each is going to be 1 times 10 to the minus 7. And similarly, if you have this as the water product, or the ion product of water, 2.4 times 10 to the minus 13, again, that's going to equal the hydronium ion concentration times the hydroxide ion concentration. So again, x squared is going to equal 2.4 times 10 to the minus 13. So x is going to equal 4.9 times 10 to the minus 6. What is the hydronium ion concentration in an aqueous solution of hydroxide ion concentration of 0.001 at 25 degrees? Okay, again, the Kw remains constant at 1 times 10 to the minus 14, and that's going to equal the hydronium ion concentration times the hydroxide ion concentration. Now we're given the fact that the hydroxide ion concentration is 0.001, and so all we have to do now is solve for the other, just dividing by 0.001. So that leaves us with a hydronium ion concentration of 1 times 10 to the minus 11. Let's talk now about amphoteric substances. Amphoteric substances are molecules and ions that may either gain or lose protons depending on the conditions. So an amphoteric substance is a substance that can act either as a Bronsted-Lowry acid or a Bronsted-Lowry base. In the top equation, the hypophosphate ion is acting as an acid in that it donates, in the condition that that one is in, it donates a proton to water to form HPO4 2- and the hydronium ion. In a different set of circumstances, the same hypophosphate would gain a proton and become phosphoric acid and the hydroxide ion. So an amphoteric substance is a substance that can swing either way. It can either be an acid in one set of circumstances or a base in another set of circumstances. Now, let's look at the concept of pH and pOH. It's extremely important that you learn this concept because there are many things that are spoken about in terms of pH and pOH. The pH scale and the pOH scale was developed for one reason. As you can see, as we've done all these different as we've looked at all these things, the concentrations are extremely small. And writing times 10 to the minus 13, 10 to the minus 12 is somewhat cumbersome. And so the pH scale was developed in order to show or to learn how or to write these very low concentrations with simple numbers. Now, neutral on the pH scale is a substance that contains equal amounts of hydronium and hydroxide ions. And you'll remember we showed in that problem that I did that that's a concentration of 1 times 10 to the minus 7, which is the highlighted band here. In that situation, the pH and the pOH are both 7. And I'll show you how that calculation is done in just a second. So anything that's acidic is something that has more acid concentration than 1 times 10 to the minus 7. And you see that's anything in this table that's superior to the highlighted band. And you'll also notice that the pH numbers become smaller and smaller as you get more and more acidic, and the pOH numbers get larger and larger as you get more and more acidic. Conversely, the basic substances are substances that have a greater concentration of hydroxide ions than hydronium ions, and these are all the ones below the highlighted neutral bar. And again, you'll notice that the pH numbers get larger and larger, and the pOH numbers get smaller and smaller. Well, what is the definition of pH? Well, pH is just a means of expressing the hydronium ion concentration. And the formula for it is given here, and it's a formula that and the pOH at the same time is the same idea, and the only difference is one measures hydronium ion concentration, the other measures hydroxide ion concentration. And these two formulas are two formulas that you really need to keep close. And you'll notice that it's a negative log base 10 of the hydrogen ion concentration. Well, if you put 1 times 10 to the minus 7 in there, the base 10 of 1 times 10 to the minus 7 is minus 7. And then the negative of that is plus 7. And so that's actually exactly how you do it, is you put the concentration in there, take the log to the base 10 of that concentration, and then the negative of that is the pH or the pOH, depending on which one you're measuring. So let's do a couple problems looking at this. What is the hydrogen ion concentration of stomach acid, a solution of hydrochloric acid with a hydronium ion concentration of 1 times 10 to the minus 3 molar? Okay, we said that pH is equal to negative log base 10 of the hydrogen ion concentration, or hydronium ion concentration, however you want to say it. So it's going to be the negative log base 10 of, in this case, 1.2 times 10 to the minus 3. Now, if we put this in our calculator, and what you need to do is put 1.2 times 10 to the minus 3, and then you select, on your calculator, you select the log base 10 button, and you'll see that that comes up as minus 2.9208. So it's minus a minus 2.9208, so the answer is going to be 2.92. Look at the second one. Calculate the hydronium ion concentration of blood, the pH of which is 7.3, which is slightly alkaline. Now we know that 7.3 is equal to the negative log base 10 of the hydrogen ion concentration. And so what we have to do is take 10 raised to the negative 7.3, and that's going to be the hydrogen ion concentration. So you look at your calculator and you put 7.3 minus, and it's an inverse function, so you find the inverse button on your calculator, which is a 10 with a little x beside it, and that gives you that this answer is going to be 5.01 times 10 to the minus 8 for molar for the concentration.